All right. So could everybody see the slides? And does the transition look okay?
Looks frozen on a PowerPoint.
Frozen?
Yeah.
I don't see a screen at all either.
Oh, it's still white or just showing? Okay, it's sharing.
I see the PowerPoint screen.
Mine just says that you've started sharing.
Okay, it's been shared. I guess for 2 minutes. How about now? Does it show up?
It's not like moving or anything. Like you're just kind of in PowerPoint without it being in present mode for me.
How about right now? I'm moving. I'm transitioning the slides. Do you see that?
Nope.
Nope.
Let me stop sharing and do it again. It's really a headache. Sorry. Can you guys see the slides now?
Not yet. It might just need time to load though.
No, still black screen.
Yeah, perhaps we still need to wait for a few seconds.
I can see the slides now.
Yeah,
Okay.
it's here.
Okay, great. So how about the transition?
Yeah, you're on maximizing margin right now?
Yes, and the max margin classifiers.
Yep.
Okay, perfect. Okay, thanks for the patience. We need to start right now, okay? So let us continue with the supervised machines, right? In the last lecture, we have introduced our philosophy or strategy of learning SVM. That is, we want to maximize margin, right? So we have justified why maximizing margin is reasonable. Actually, there is a chain of logic, right? A logic chain. If you don't recall, right? Just because, so basically speaking, we're not searching over the entire family of linear classifiers. If we do that, the VC dimension of the entire linear classifier family is fixed. It's D+1, where D is the dimension of input space, right? So, and we know that the generalization error bound is determined by the training error plus some term determined by VC dimension, right? The smaller the VC dimension, the tighter the bound, or the smaller the bound, right? So, therefore, to reduce the bound, right? Reduce the bound of the generalization error. We want to reduce the VC dimension, right? So we want to pick up a small subset of linear classifiers as well as our hypothesis space, and we search over that hypothesis space. In that sense, we're going to decrease the VC dimension of hypothesis space, right? And then we introduced ideas called data-dependent VC dimension. So we can define the subset of linear classifiers in terms of the margin for a specific data set. Right here, we just use our training set. So according to some theory proved by Vapnik, we know that the larger the margin, the smaller the corresponding VC dimension of the linear classifier subset, right? So then it drives us to find the linear classifiers who has the largest margin, right? Because that corresponds to a subset of linear classifiers who has the smallest margin, which corresponds to the smallest upper bound of the generalization error. That means that we expect our true error will be small as well. Right? That's the whole chain, right? So I highly suggest everyone to kind of review how we reasoning about the the method or the strategy to learn SVM is actually rigorously justified by the generalization error bound from the agnostic learning setting, right? So then, after we have knowing that, okay, our goal is to maximize margin, right? We need to turn this strategy into some actionable optimization problem, right? So our naive formulation is according to the original definition of margin, right? Margin is the distance of the closest point from the hyperplane. So if you write it down as a mathematical formula, you're just minimizing the distance across every training examples, right? So this is a formula to calculate the distance between arbitrary point and the hyperplane determined by the weight vector W, right? And then in the outer level, we're going to maximize this margin with respect to W and B, right? In the inner level, given W and B is fixed, we need to go over every training example to calculate the margin, right? But doing this is kind of performing a max min, like two-level, bi-level optimization problem, which is quite challenging, right? We mentioned that in the last lecture is actually finding a saddle point problem is not easy, and also for every change of W and B, you're gonna go through every training point and to find a corresponding margin, which is very costly, right? So then we make an important simplification trick, right? So this trick comes from our observation in that because the linear classifiers will only care about the sign of the prediction score, right? We do not care about the magnitude of the parameters like WB, right? You multiply WB by arbitrary positive scalar, 0.001 to 1 billion. It doesn't change the classifier, namely the classification boundary at all, right? So that means it's not necessary for us to search over the entire space for W and B, right? We can restrict them to be a very small subset, but arbitrary WB setting, you can find the equivalent setting within the small strings by the corresponding scaling. That's the key idea. So how can we restrict the search space? We simply restrict that the minimum value of this numerator is to be 1, right? We choose W and B. The set of WB, which we're going to optimize over, is the set of WB whose minimum value over all the training examples of this numerator is simply 1, right? This minimum value is also referred to the functional margin, right? So we have explained, right, the equivalence for any WB outside of this small subset, right? So this small subset, any WB values will satisfy the minimum function margin. The function margin is simply 1, right? So for any WB setting which is outside this this small subset, you can divide WB by the corresponding function margin. You actually find an equivalent setting of WB inside this small set, and they correspond to exactly the same hyperplane. Right? That's the whole rationality. So, and then by doing such kind of simplification, namely we're restricting search space of W and B, the benefit is that we, in our objective function, will no longer need to minimize over all the training examples. Right? Our optimization problem becomes one level. Right? We only need to maximize because the function margin is simply 1, right? We only need to maximize 1 over the norm of W, right? So, and then we formulate our optimization problem, right? For our SVM. So the learning problem is equivalent to minimize half W transpose W. This is actually the square of the norm of W, right? And because you want to maximize inverse or 1 over the norm of W, it is equivalent to minimize the norm, right? And we multiply this half is just to similar to you place a half in front of the objective function for the linear regression, least mean square regression, right? It's just for convenience to cancel the actual factors, right? If you take the gradient over W. And then because we restrict the search space of W and B to to be the set that whose function margin is no less than 1, right? Is 1, right? That means we need to put extra constraint, right? And such that for every training example, this value, this product is no less 1, right? So because this is numerical, it corresponds to numerical, right? That means, okay, yi times this prediction score is no less than 1, right? So, and then because the gamma, the margin, right? Margin is minimum value of this, right? So we know that, okay, it actually implies that we're restricting W and B in that set whose function margin is 1, right? So this is called hard support vector machine. And although this kind of like faithfully recover our philosophy of maximizing the margin, right? There's a big issue, right? The big issue is that, okay, you're gonna assume the data is linearly separable, right? Of course, the data is linearly separable, okay, it's okay, right? But the realistic world is not like that, right? In most cases, actually, what we expect is that, okay, they're almost linearly separable, right? There could be some examples, right? And some outliers, some anomalies, such that because of their existence, you'll never be able to find a hyperplane that will separate all the positive and negative examples. Right? In that case, that means you cannot always satisfy those constraints for every training example. Then you solve this optimization problem, you're gonna give no feasible solution, right? And how can we address this problem? Right? And then here comes our the final objective for SVM. It's called soft SVM. Right? Soft SVM was proposed to deal with all kinds of cases. Even your data set is not linear separable, you can still can learn a working well linear classifiers. Right? So what's the key idea? The key idea is that to compromise the reality, right? Now that the data set can be nonlinear separable, right? So we want to design a mechanism such that we can allow some example to break into the margin. In other words, I want to automatically find a majority of examples which are linearly separable. We only find a linear classifier that maximizes the margin for that majority subset. Right? And for the remaining a few examples, which we refer to as outliers, will allow them to break into the margin. So this is the key idea. So an intuitive explanation is here, right? So we can take a look at this particular data set, right? We see that, okay, looks like most positive and negative examples are well separated, right? Except a few outliers, right? But unfortunately, this data set can only be claimed as almost linear separable. It's not linear separable. You can never find a linear classifier which can perfectly predict every example, right? Then where can we do that, right? So our idea is that, okay, we want to design an objective function which can automatically exclude these two outliers, right? Circle examples, right? And for the remaining examples, the remaining majority which are linearly separable, we find a classifier who has the largest margin, right? And we only leave these two outliers. Okay, we'll allow them to break into the margin, right? So we see that, okay, the positive examples this breaks into margin, right? For negative examples, it is here, right? So if it should be correctly classified, it should be stay here, right? But unfortunately, it breaks into margin and moves to the other side. That means, okay, we'll allow some non-zero training error. Right? And then the problem is that, okay, how can we fulfill this idea, right? How can we encode this idea in the formulation of our objective function? So, this is hard SVM, right? And now, first step, right? So we know that from the hard SVM constraint, we require every example has a function margin at least 1, right? So namely this product, right? This product is at least 1, right? So of course, if every product, if the example, for every example, this product is no less than 1, meaning that, okay, every example is on the margin, outside the margin, is correctly predicted. Right? So, and then how can we relax this constraint? Or in other words, how can we allow some example to be to break into margin? Right? We introduce a select variable Ci for every training example. We require that Ci is no less than 0, and then we modify our constraint to be this product is no less than 1 minus Ci. So now I want to ask why Ci must be non-negative. Any thought?
Otherwise, the margin will be higher.
Yes, exactly right. Thanks, Tusha. Yeah. So if we want to some example to break into the margin, that means this product, this functional margin, is less than 1, right? It could be less than 1 or even less than 0. If it's less than 0, that means then it's not only like example here, right? Like this negative example, it not only breaks in margin here, it also flips the side, right? It comes to another side, right? Or for the positive example, okay, I mean, okay, it is inside this margin, right? Inside the margin meaning, okay, that product or yi times prediction score is less than 1, right? If it is 1, meaning that, okay, it stays on the margin. If it is bigger than 1, means it's outside the margin, right? So now if we take a look at here, right? If Ci is less than 0, and then that means that I put an even stronger requirement that your functional margin is bigger than 1. It means that, okay, your points, your example must be stay strictly outside the margin, right? That is even stronger requirement. But here we want to relax the requirement. We want to relax the constraint that we allow some examples, according to the data, they can automatically choose to break into the margin. Okay, so intuition here, right? Let me emphasize again, right? The select variables allow the examples to break into the margin, right? So if the select value is 0, that means our constraint return to the hard SVM case, meaning that, okay, the example is either on the margin or outside the margin. So now we have modified the constraint, right, to be more flexible. Right? And then we also need to modify the objective function. So in the objective function, in addition to this half square norm of W, we add one more term, which is a hyperparameter C times the summation of all the select variables. Right? So remember, the select variables comes from here, right? So it is a non-negative, and it allows us to it allows some example to break into the margin, right? So now my question is, why in our modified soft SVM in objective function we need to add this extra term? Right? Why not we just maintain the same objective as in hard SVM? We just modify the constraint.
Well, I think if we're measuring the objective, right, to kind of say how good our algorithm is doing, and we have points that are completely on the other side of the line that are like mispredicted, wouldn't that be problematic?
Yeah, it sounds right. Let me make a comment later. I want to ask if anyone can give more thought. or supplement? Okay, yeah, but anyway, that's enough. Actually, you hit point. Correct. Yeah. Why? Because we need to account for this, right? We do not want all the examples to break into the margin. We want to also minimize the total slack variables. That means we want to most example to be correctly classified by our linear classifiers. Why? Because remember our generalization error bound, right? The generalization error bound is determined by two terms, right? Not just term determined by VC dimension, right? You have two terms. One is the training error. One is some extra term which can be viewed as a function of VC dimension, right? To make your error bound, the true error bound, to be as small as possible, right? You not only need to reduce the VC dimension, but you also need to reduce the training error, right? If you don't put this term, right? If you don't add this term, right? It kind of encouraging, right? You exclude most of training examples, right? You allow them to break into the margin. You only find the margin for a very small subset of example. In that case, okay, like if we look back, right? If we look back at this example, right? So if we do not add the summation of slack variables in the objective function, what will happen? Happens that, okay, because I want to maximize the margin, right? So why not we just exclude, we just find out two furthest point, right? See, this 2 point, right? And then exclude all the other examples, right? We will allow them to break into margin. We just find a hyperplane which has the largest margin which can separate these 2 points here, right? Because they're the farthest. That means you can get the smallest VC dimension, right? But what is the price? The price is that you're gonna misclassify a lot of training examples, right? You'll give a much larger training error. And as a result, right, although your term determining the VC dimension is reduced, your training error increases, right? You add them together, your bound still, your bound will still be increased, right? That's the idea. So the idea here, we add this objective function, a summation of the slack variables, is to find a trade-off. I want to make the classifiers to have a large margin, to have a larger margin as large as possible, right? For a set of training examples. At the same time, I do not want many training examples to break into margin and give wrong classification results. And then overall, I want to tighten the generalization error bound to be as good as possible. Okay, any?
And yeah, so is C just then like just some parameter we can use to essentially just scale how much that's going to influence our optimizations? Like if,
yes,
I guess if, then you could make it have a higher penalty or whatnot.
Yes, exactly.
Okay.
Exactly. Yeah.
Cool.
C here is a trade-off from. I'll say that later, right? So let me just summarize, right, the meaning of these two terms, right? So the first term, half the W transpose W, is kind of a regularization term. I want to encourage your linear classifiers to have a margin as large as possible, right, for a subset of training examples. If your data set is if the whole data set is not linearly separable, right? At the same time, I just want to allow as few examples as possible to violate margin, so that I want to maintain a high training accuracy or small training error, so that overall the true error bound, which is summation of the training error plus the term determined by VC dimension, to be as small as possible. And here, as what Jonathan said, right, C is a trade-off between two terms, and unfortunately, I can now tell which is the best choice. You really have to tune it by yourself, and it is dependent on different applications. I mean, different applications, you might have different choices of the C. And you will see that in our next homework, you will be required to tune different values of C and see how the choices of C will affect the learning performance. Okay, any question regarding the understanding of the formulation of soft SVM? Great. So now let us further simplify the optimization of this formulation, right? So of course, this is a kind of like, constraint optimization problem. It's not easy, right? It's not easy. So we want to first simplify it to say if we can eliminate this constraint, right? How can we do that? We can try to eliminate the slack variables. How? We can observe that for every training example I, we have two constraints, right? The first is the function margin is no less than 1 minus KCI, and also KCI is non-negative. So if you just simply change the direction of the inequality, we get KCI must be no less than 1 minus this function margin, right? At the same time, KCI must be no less than 0. And remember, in the objective function, right, we want to minimize W transpose W and also every value of KCI, right? So now we know KCI has two lower bounds, right? One is 1 minus function margin, the other is 0, right? So of course, if we want our objective function to achieve the minimum, we need to choose the minimum value of the two, right? Or maximum value of the two, because you need to satisfy both, right? So the KCI, its minimum value is maximum of these two lower bound, and then we can simply replace KCI by the maximum of its lower bound. And in this objective function, in this way, we simply just get rid of all the constraints, right? And then we only need to optimize this unconstrained objective function. So any question regarding this? Okay, so before we talk about how to optimize this function, right? We're going to talk about stochastic gradient descent again, right? Let us first look at the structure of this formulation. Actually, the structure of this objective function reflects an even more general framework to design your learning objective. So if you look at this objective function, it contains two terms, right? So the first term is half W transpose W, which requires us to maximize margin, right? And the second term is actually a summation over every training example I, right? This is a summation over I, right? And every term regarding the training example I actually reflects a penalty for the prediction. So how can we will it as a penalty, right? We can look at three cases, right? So first, if this example is correctly classified and outside the margin, what's the value of this? What's the value of this max function?
0.
Yeah, 0, right? Because first example is correctly classified and outside margin, meaning that, okay, this function margin must be bigger than 1, right? If it is equal 1, means, okay, it is just touch the margin, right? Remember, in our constraint space, the minimum function margin is always 1, right? If it's bigger than 1, means that, okay, it's outside the margin, right? So that means 1 minus something bigger than 1 is negative, and your max value is 0, right? That means, okay, your penalty is 0, meaning that, okay, if your example is correctly classified by the current W, and is also an example is placed outside the margin, okay, you pay no cost. Your penalty is 0. And second case is that okay, your example is misclassified. If your example is misclassified, that means this value, this product, or other words, function margin is less than 0, right? We have discussed the this meaning, the equality of this meaning many times, right? If this product, the ground truth label multiplied the prediction score is less than 0, it always indicates you misclassify this example, right? I mean, this product is less than 0, 1 minus some negative value is bigger than 1, right? Bigger than 1, that means this max value 0 and some value bigger than 1 will be the latter, right? So you got your maximal value function to be 1 minus this product. So you can see that because our goal is to minimize this objective function, right? If you incorrect classify the example, you have a bigger value, right? That's why we call it a penalty, right? You pay some kind of cost. Your cost is this 1 minus functional margin. And we have a third case. The third case is that, okay, we have correctly classified the example. However, this example stays inside the margin. It's like that, right? Suppose this is our hyperplane, and this is the margin, right? And suppose this is W, right? Sorry, I didn't. So this is orthogonal, right? I'm sorry. Forgive my bad drawing, right? So this is a positive example, right? So this is a positive example. Okay, we can correctly classify examples because this product is no less than 0, right? However, this product is so small such that this example is inside margin. Then the value of this max function is non-zero. Why? Because when it's inside margin, that means this value, this product, this function margin is less than 1, right? 1 minus something less than 1 is still bigger than 0, right? The max value is still the latter. So you still pay some cost, which is 1 minus the function margin. So we can see some interesting point here, right? If you correctly classify the examples and your classifier is kind of far away from the example, such that the example is outside margin, you don't pay any cost, right? Penalty is 0. If you incorrectly classify example, well, you definitely pay some cost, which is 1 minus the function margin, right? However, in the third case, even you have correctly predict this example, right? But your classifier, if it is too close to this example, such that you allow this example to break into margin, you still pay some cost. This is kind of like unique property of the max margin classifiers learning. It always encourages you to get away from the examples, training examples, and the further away, the better. The less penalty you will pay. Okay, so we define this max function a loss function, and this loss function is called Hinge loss. It's a very famous loss function. So loss function is defined for a training example, right? So it's max between 0 and 1 minus the product between the ground truth label and the prediction score. So any question regarding the analysis of this? Everyone feels comfortable, right? Okay, great. So let us just look at some like more intuitive observation of loss, Hinge loss, right? So ideally, when we construct loss function, right, we want that if your prediction is wrong, meaning that this function margin or the product between the label and the prediction score, if it is less than 0, you pay some loss, right? You incur some loss. You're penalized because you make wrong prediction. So the loss is 1. And if, for example, right, if you make a correct prediction, meaning that this product is no less than 0, right? And then you don't pay any cost, right? Your loss is 0. But unfortunately, this loss, which is called 0-1 loss, often viewed as the oracle loss in the computational learning theory, is very hard to compute. It corresponds to some kind of, if you want to optimize it, you have to incur some kind of combinatorial search. It's very hard, right? So people have come out many surrogates, right? So one popular and theoretically justified surrogate is called Hinge Loss. Right? So if you look at the curve of Hinge Loss in terms of function margin, right? In terms of this product, it has such a curve. It's actually an upper bound of the 0-1 loss. So you see that only when your function margin is bigger or no less than 1, right? You have no loss because you correctly predict the example and your example stays outside margin. Right? And if you correctly predict examples, but your hyperplane is kind of too close to the example, such that example breaks into margin, you still pay some cost, right? You have non-zero loss here, right? And the loss increases as your example is closer to the classifier or the hyperplane, right? If it is too close, right? Say if this is your hyperplane, right? This is your margin, right? Your example is here. You actually stay in this region, right? You see in this region, you incur some loss, right? If you're getting closer and closer to the classification boundary or hyperplane, you incur larger and larger loss. You can see that. And on the other extreme, right? If you go to the other side, right? You make a wrong prediction and even get further and further away. I mean, meaning that you make a more and more wrong predictions, right? You incur larger and larger loss. So that's the behavior of Hinge loss. Someone may ask, right? Do we only have the choice of Hinge loss and 0-1 loss? The answer is no, right? You can come out actual loss as long as you can justify it or show some effectiveness, right? So I'm gonna skip this because it just re-described what I have just said, right? You actually can add actual loss, as we will see later, right? We have an actual zoo of loss, right? You have different loss, which correspond to different models and correspond to different justifications, right? So, okay. So any question regarding the regarding our discussion about Hinge loss and the definition? Okay, so now from this formulation, right, we can abstract it and to summarize two design principle of learning objective, right? One is called risk minimization. So what is risk? Risk here is defined to be a loss. What is risk minimization? I define some kind of loss over the trained data, which is typically a summation over each loss, over the loss of each training examples. And then the goal is to minimize the summation of the loss over the whole training examples. This is called risk. This is called to minimize the risk. And the learning is to find the hypothesis that has the lowest loss on the training data. And then what's the problem of this idea? Any thought? Or if you apply risk minimization principle to design a learning objective, right? What's the consequence? Do you feel anything harmful or anything bad? Imagine that we're trying to only minimize the loss, the training loss, like over the whole training set, right? And then we have two hypothesis spaces, right? One is more expressive than the other. Say I have a simple hypothesis space and a much more complex hypothesis space. And which hypothesis space will be more favored?
A complex one, so it might not generalize to the test set.
Yes, exactly right. Remember, we want to apply our Occam's razor principle, right? But if you just perform risk minimization, meaning that, okay, I just want to better fit the training data, that means we're gonna always favor more complex hypothesis space because they are more likely to give you smaller training error, right? But as we said, right, using over complicated hypothesis spaces might affect the generalization error. This is what the generalization error bound tells us, right? The larger the visit dimension, the larger the bound of the true error, right? And then a more conservative and more favorable principle comes out, right? It's called regularized risk minimization. So the objective under regularized risk minimization principle usually has two terms, right? The first term is a regularization term, which is to penalize over complex hypothesis spaces. So that we want to express that our favoring is for smaller or less expressive hypothesis space, so that we can have a smaller visit dimension, right? And on the other hand, of course, we need a training loss term, like to ensure that we get a small training error. Remember, our generalization error bound is determined by the summation of the training error and some term determine the visit dimension, right? We want to find the best trade-off to make our bound to be as small as possible. So the learning then is to find a hypothesis that has the lowest regularization plus training loss. The particular example for this regularized risk minimization principle is the Svm objective function. We have two terms. The first term, this square norm of W, regularizes the complex of hypothesis space. Is actually search for the subset of linear classifiers who has the largest margin, right? So we want to maximize margin, and we know that connection between margin and visit dimension, right? The max margin index the subset of linear classifiers who has the largest margin, who has the smallest visit dimension, right? And meanwhile, we have this Hinge loss. This Hinge loss also shows how we fit the training data, right? Of course, the smaller the Hinge loss, the smaller the training error, right? And finally, we have a hyperparameter C, which controls the trade-off between the two, right? And again, in practice, no one tells you which is the best choice of C. You need to manually tune it to fit your own application. Okay, any questions so far? Is everybody comfortable?
Sorry, yeah, just to restate this. So you're saying, because like, I guess the way we kind of got to this, you're saying if we just evaluated, if we just wanted to minimize risk, we would only be minimizing this empirical loss term.
Yes.
Okay. And then you're saying by incorporating the square of the norm of W, then we're able to essentially, we're incorporating this regularization into it. Okay.
Yeah. So actually this idea you will see, I mean, in the future, if you want to dive into the machine learning area, you will see nearly all the machine learning models and algorithms reflect such kind of trade-off. If you want to resist overfitting, or you want to penalize over complex hypothesis spaces, what do? Right? Add some regularization term. And the robust and well-performed machine learning models will always have these two terms. And how we choose the trade-off between them, smarter choose them. And someone may ask, okay, why should we stick to Hinge loss, right? Of course, you can switch it to other loss. You can choose it to be square loss or whatever loss, right? And If it is not linear classifiers, you do want to penalize the complexity of a classifiers through the margin, right? You can define other regularization term as long as you can justify. Okay, it corresponds to small base dimension. That's fine. Okay, so we have finished the formulation of the SVM objective. Our next step is going to discuss how we learn them, how we optimize the objective function. So let us switch to other slides. Can you guys see the slides? Support machine is training with stochastic gradient descent. Does it show up?
We see the slides, but you're not presenting yet.
It's too slow. How about now?
We can see the presentation now.
Okay. So do you see the transitioning?
Yes.
Okay, great, perfect, thank you. So, okay, so now the remaining things regarding support vector machine is how to conduct training, right? In other words, how do we optimize the objective function in SVM, right? So we're gonna first talk about the training in the primal domain. We're gonna talk about stochastic gradient descent again, right? So this is our third topic in the outline, is solving SVM optimization problem, right? So if you look at, this is just go back to this SVM objective function again, right? So it has two terms. One is regularization term. The other is a Hinge Loss term. And you have a trade-off constant C. You need to pre-specify. Okay, so we're going to talk about how do we optimize this, right? How do I optimize this objective function to find W and B, right? This will be our final parameters learned from data, right? So that will involve the optimization problem, right? This is actually a convex optimization problem. So to discuss some efficient method, right, we're going to first review the concept functions definition and the gradient descent framework. I bet everybody has had that experience, right? We just need to briefly, quickly refresh our mind, and then we'll review the stochastic gradient descent framework, and we just compare with gradient descent and stochastic gradient descent. We'll talk about their advantages and disadvantages of each other. And right now, this time we're gonna give a more thorough, more in-depth discussion, and then we'll talk about the major issue here. So you'll find that actually the objective function of the SVM is not differentiable because it's not continuous. And then how can we calculate some surrogate or substitute for the gradient, right? We call this surrogate as a sub-derivatives or sub-gradient. And we give a definition, what is sub-derivatives? And then we just replace gradient or stochastic gradient by stochastic subgradient in a canonical stochastic gradient descent framework. Then we can conduct our stochastic training of SVM. And finally, we're gonna compare the whole framework to perception. We'll see the learning, the mystic-driven algorithm in perception has a striking similar algorithm steps as SGD for SVM. And we'll find that actually perception is essentially optimizing another objective as well. And then finally, we'll make clear of this connection. Okay, so first, let us give a brief review of Commax functions and gradient descent framework. Hopefully, everybody won't feel strange on that, right? So first, this function is convex. Right? It's convex in both W and B. And I'm gonna ignore the proof, and I will leave that as an exercise for you. Right? And you should be able to use the definition or use the property of convex functions to show that this objective function is convex. Right? And for convenience, we're gonna come back to our simplification trick again. We use W naught or W0 to represent the V vector, and then we fold the bias parameter B into the whole V vector W, right? And W is a concatenation of the W naught and B, which we denote as W. And then for each training input xi, we're going to augment it with a constant feature 1. In this way, we can rewrite our objective function in this way, right? So our variables that need to be optimized is now just represented by one vector W, which consists of both the original feature with W naught and the bias parameter B, right? And the first term, the regularization term, remember we just changed notations, right? This is about the norm of the D vector about the features, right? So it's W naught transpose W naught. And here, because we use the notation simplification, right? The prediction score is not just the one in the product, right? The augmented weight vector W, right? In the product with the augmented feature vector xi, and then multiply with yi. Okay. Any questions so far? Okay. So now let's recall the definition of convex function. If we say a function f is convex, that means for every input in the domain, say u and v, and for every lambda value, which is between 0 and 1, we have the function value of this linear combination by lambda at u and v is less than or equal to the linear combination of their corresponding function values. Right? So basically, this can be summarized by this inequality, which is called convex inequality. Right? And to visualize it, this is a typical convex function. Right? This is a blue curve. If you take an arbitrary two inputs u and v here, right, and the corresponding function values are here, right, f of u and f of v, right, and if you take up arbitrary lambda, right, say here, right, so the function value of this convex combination of u and v will be here, right, but the convex combination of the corresponding function values at u and v will be here, right. So obviously, let me explicitly draw it. So here is the convex combination of u v according to lambda, right? So this is the function value of the convex combination of the inputs, right? But then on the right-hand side, right, the convex combination of the function values at u and v will be here. So obviously, the latter, right, the right-hand side is bigger than the left-hand side, right? So this is called convex function, and this should be satisfied for arbitrary two pairs of the inputs u and v. And another interesting property comes from a convex function is that, right, if this convex function is differentiable, right, and we know this inequality is always hold, right, what does this inequality mean? Right? So for arbitrary function value at x, right, an arbitrary function value at u, right, we always have this inequality that f of x is bigger or equal to f of u plus the inner product between the gradient of f at u and x minus u. So what does the right-hand side mean? Any thought?
Does the right-hand side describe that line that's tangent?
Yes, exactly right. So you imagine this is just a two-dimensional plane, right? It's just x1 plane, right? This actually defines the tangent line, right? So the gradient if you take a look at this input, we denote it as u, right? The gradient of f at u is just the slope of the function at this input, right? And then this form actually defines a line, right? Defines a line. So suppose this is the x-axis, right? It just defines a line. So this inequality just means, right, this is f of x, right? Just means every function value is bigger than the value at this tangent line. More specifically, that means the tangent length always lies below the whole function. That's another interesting property of convex functions. Like you can try any other position, like say here, right? If you draw a tangent line, right here, right, you see that. Sorry, my drawing is bad, right? But we can still see that actually the whole line still stays below the whole function curve. Right? And say if you draw a line here, right? Same thing, right? It still stays below the whole function curve. That's the interesting property of the convex functions. So here are a few common saying examples for convex function. So first, linear functions are both convex and concave, and later we'll see what is concave functions, right? And the quadratic function is convex, and max of 0 and x is convex as well. So another subtle thing about definition of convex functions: convex functions do not necessarily are not necessary to be continuous. It can be not differentiable. It's fine as long as at every input pair you satisfy this inequality. It is convex. It's not necessary to be continuous to be differentiable. Like convex, like max function is a convex function. You can show this by using the definition. Right? So here is another example, like function of two variables. Right. This corresponds to a cone. Right. So there are several common ways that I use to show a function is convex. First, using our original definition, right? As long as you can show that convex inequality always holds, it's a convex function. And if this function is differentiable and secondly differentiable, right? What you can do is just show the second derivative is non-negative, right? If it's one-dimensional. Right? If it's a vector function, meaning the input is vector, right? You just need to show the Hessian matrix is positive semi-definite. I believe everybody has practiced that in our very first homework. So someone may ask, right, what if I just reverse the direction of this convex inequality? If the function instead have always satisfy this inequality, right? The function at the convex combination of the inputs is bigger than or equal to the convex combination of the function values at the inputs. This is called concave function. Actually, you just put a negative sign in front of all convex functions, they become concave functions, right? Here are several examples, right? First, linear functions are concave as well. So actually, you can see that linear functions are both convex and concave. Why? Because for linear functions, we have an equality here. We don't have strict positives, don't have strict negative, we have equality. So it satisfies both equations, right? Both inequalities. And this negative quadratic function, this minimum function. But there can be some functions that are neither convex nor concave, like this. This function look like sine functions or cosine functions. They are not convex. They're not concave. Or this piecewise function is not convex or concave. Right? So basically, convex function or concave functions, they only include a very small set of functions. Right? They do not represent a lot of like all kinds of weird and rich functions. Okay. So, but why do we care about a convex function, right? So you see that in machine learning area, convex functions take a very, very important role. The reason is that the convex functions have many nice properties. Like one example will be if you find a local minimum of a convex function, like this projective function, it corresponds to global minimum. It's not like some non-convex, non-concave function like this, right? You have a lot of like local minimum, right? If you find one place where you have a local minimum, it does not mean you find a global minimum. You might have an even better minimum here. But for convex functions, it either doesn't have any minimum or like a line, right? A line doesn't have any global minimum or global maximum. If it has a local minimum, you have unique local minimum, which is the global minimum. Okay, so in addition, I want to I want to review a commonly used condition to test to say if we optimize a function, an arbitrary function, if I have found minimum. Right? So we have a necessary condition, meaning that if some x is a minimum, it could be minimum, local minimum, it could be global minimum of that function, and the function is differentiable, then the gradient of the function at x will be 0. This is the only necessary condition. So now one asks why it is not a sufficient condition. In other words, can we see that if we have this gradient of function at x 0, x will definitely correspond to a local minimum. Will definitely correspond to a local minimum of function. Any idea? Let me repeat it again, right? So we use this condition, this testing condition by default, right? So we want to check if we find x such that reaches some local minimum of the function, right? We just test if this gradient is 0, right? But here I want to highlight this is just a necessary condition, meaning that if x is a local minimum, then the gradient is 0, right? But if we reverse this, is that still true? Right? In other words, can we believe that if the gradient is 0, then we find a local minimum?
No, because couldn't it also just be a maximum?
Yeah, exactly, right? So that's why it's just a necessary condition, right? It can be local maximum, it can be local minimum, and even worse, it can be neither a maximum nor a minimum. So here I want to emphasize there's a case, it's called a saddle point. The saddle point means that, okay, you still have a gradient here, right? You still have a gradient here, means the gradient, 0 gradient here, right? The gradient here is 0, right? But x does not correspond to any local minimum or any local maximum. Of course, we don't want to meet such kind of point. But a very good property of convex function is that this is both necessary condition. It doesn't contain any saddle point, meaning that if you have a global, if you have a minimum, then you must have gradient to be 0, and vice versa. If you have a gradient to be 0, it must be a local minimum. So this is a necessary and sufficient condition. Okay. So now let us look back at this Svm objective function, right? So as we just mentioned, right, this is a convex function, and it's pretty easy to show that the first term, the quadratic function, it is convex for sure, right? And the second one is max function. And inside max function is a linear function. You see that according to some nested condition, right? If you have a convex of a convex function and the inner convex function is kind of monotonically decreasing or whatever, right? You can check, you want to double check the condition. You can show that that function will be convex as well. And the addition of two convex functions will be convex, right? So it's pretty easy to show this whole objective is convex, right? And this convex function corresponds to a classical type, which is called quadratic function. Right? You can optimize with this so-called quadratic programming. Well, this is kind of like off the shelf, right? The quadratic programming is kind of off the shelf algorithm. The issue is that this is very slow. We don't want to call that kind of library. Right? Instead, we want to use the simple framework we have used before, the gradient descent. But the problem is of gradient descent is still very slow. Right? We mentioned that problem before, right? So if you want to calculate the whole gradient, right, you have to go over every training example, right, to calculate one gradient to perform one update. This is very slow, right? So later we'll switch to the stochastic gradient descent, right? But let us first briefly review the gradient descent framework. Right? So here's the general framework for gradient descent. Suppose I have a objective function j here, right? And we're gonna start with some initial guess for w, we denoted by w0, right? And we'll just iterate until convergence or the maximum number of the updates have been finished, right? Inside each iteration, I'm gonna first compute the gradient of the objective at current input or the parameter vector denoted by wt, right? And then we update wt to get wt plus 1 by taking one step in the opposite direction of the gradient, right? Why? Because gradient direction indicates where we're going to increase the function, right? If we want to decrease the function, right, minimize the function, right? Want to decrease the function value every step, we need to follow the opposite direction of gradient, right? That's why it's called gradient descent, right? So here we just look at the previous example again, right? This is a simple example showing the objective curve JW, and this is our initial choice of the W, right? W0. And when we calculate the gradient, which is slope of this function, right, is positive, meaning that the gradient is along this direction, right? And then we need to follow the opposite direction of the gradient to reduce the function. We get W1, right? We indeed reduce the function value. And then we calculate gradient again, which is slope, which is still positive, right? And then that means we need to move in the opposite direction and we get W2, right? We do it again and again until we converge or the maximum number of the iterations are done. Right? So this is a gradient descent, and if we just apply this gradient descent in learning the in optimizing the Svm objective, here is the whole framework, right? So we initialize the weight vector W0, right? Remember this W0 contains both the feature weights and bias parameter. And go through each iterations from 0, 1, 2, 3, 4, 5 until the stopping criterion is met, right? Inside each iteration, we compute the gradient of the Svm objective function here, right? At the current weight vector, Wt, right? We call it the nabla J of Wt, then we update the weight vector as follows, right? With the Wt plus 1 is obtained by subtracting current weight vector Wt by some learning rate multiplying the gradient of the objective. Okay, any question regarding this framework?
Will we be expected to implement this?
No, no. We won't want to implement this. This is kind of like simply replicate what you have done for the least mean square. Right? We just want to refresh our mind because we're gonna look at the stochastic gradient descent framework.
And will we be implementing stochastic gradient descent for SVM?
Yes.
I see. Cool.
Any other question? Yeah, I assume this is just a quick review. Okay, great. So now let us look at the stochastic gradient descent, right? So what is stochastic gradient descent? It was motivated by the fact that the update of the gradient descent is too slow. Why? Because to calculate every gradient, right, we have to go through every training example here, right? So suppose there are 1 million or even 1 billion training examples, right? To calculate one gradient, to update once, right? You have to go over all the 1 million or 1 billion training examples. It's really, really slow. Right? So how do we accelerate update, right? We want to say several examples will update many times, right? And in this case, we're going to use the so-called stochastic gradient descent. Why is it called stochastic gradient descent? Because here we're going to use some approximate to the true gradient. That is, we're going to go through the whole training set multiple times, which we refer to multiple epochs, right? Suppose we set the maximum number of epochs to be big T, right? And inside each epoch, we're going to random pick up a training example from the training set S, right? And then we just duplicate this example xi, yi, right, to make a full data set, meaning make the data set with the same size as our original data set. Like the original data set includes 1 million training examples, right? So right now, I just pick up one example. I duplicate it for 1 million times. So that will create a duplicated data set, which has the same size as the original set. And then I use this fixed data set to calculate the gradient. And then calculate gradient over the whole objective of the fixed data set. Because each training example, every training example is the same, right? So you just need to calculate the gradient for one example, and then calculate loss for one example, and then multiply by the size of the trained data, right? And then as the regularization term, we got the objective function on the fixed data set. Then you calculate, so n here is number of training examples. Then you calculate the gradient of the objective over this fixed data set, and we refer this gradient as stochastic gradient. And then we just update our parameters W with this stochastic gradient. So any questions so far? Notice there is some kind of difference from the previous stochastic gradient descent you have seen, right? So the previous stochastic gradient descent is applied for the least mean square, right? Our loss function is just the summation of the square loss over every training example, right? We don't need to repeat or duplicate the sample the training example, right, multiple times to fit the whole data set. We just need to randomly sample one example and just calculate the gradient of the loss over that particular example. Then we use that as our stochastic gradient, right? But here, we make a little bit trick, right? A little trick. What is, we need to first repeat our sampled example for n times. And we construct a new objective, right? This objective is the regularization term plus the loss on this particular example multiplied by the number of training examples. Right? It's just equivalent to duplicating this random sample for n times to create a fixed data set, and then calculate the whole loss over this fixed data set. And why should we do this? So here we want to explain a little bit, right, in general, how we conduct stochastic gradient descent. The reason we don't do that for the least mean square is because the objective function doesn't contain any regularization term. It's just a training loss, right? You don't need to skew the loss by a constant number. But here, because in addition to the training loss, you have some extra regularization term, right? To maintain the same skew, you have to multiply the loss for this single example by the size of trained data to maintain the same skew. Only doing that can ensure that your approximate gradient is unbiased stochastic gradient. So here,
I have a question about that. So the 1/2 W0 transpose W0, what does that W0 represent? Is that like our current weight vector, or is that the weight vector we started with at the very beginning?
oh, no, it says the weight vector excluding the bias parameter.
Oh, excluding the bias.
So remember we previously mentioned, right? So we changed the notation, right? So here the weight vector contains all the feature weights plus a bias parameter. So W0 here.
Okay. So we haven't. So W0 don't have the. Okay.
Yeah, W0 doesn't contain the.
And that's in this example, right? So.
Yeah.
So it's a subset of the weight vector, but it is our current weight vector, right? So.
Yeah, it's current. It's current.
Okay.
Yeah.
And then
current elements in W. W is current weight vector.
Gotcha. And with JT, right? That we're JT of W that we're calculating here, right?
Yes.
How do we use JT to then update our weight vector?
Okay. You just calculate the gradient of JT and apply the gradient descent. So if you write it down, it will be like this, right? W equals to W subtracted by some learning rate times the gradient over the JT. Okay?
Okay. And so we have to, the gradient of JT of W, like that would be the derivative or something? Like, you know,
yeah, the derivative, the gradient, whatever. But just notice that the gradient of GT is not the true gradient, right?
Right.
The true gradient is you're gonna go through every training example to calculate the gradient, right? But here we just pick up one example, calculate its loss and multiply it by n.
Right. I guess like in terms of actually implementing this, I would want to know like how we'd calculate the gradient of JT of W, just kind of like more strictly, so that I don't have to figure out.
That's a very good question. We're gonna address, I guess, on Thursday, right? This is actually doesn't have gradient. This maximum doesn't have gradient, right? We need to seek for the sub gradient.
Okay, so it gets a little more complicated before we can figure out exactly how to update this.
Yes, exactly.
Gotcha.
Okay, thanks. Let us continue on Thursday. And on Thursday, we expect to finish the learning part of SVM for the primal domain. We actually have another domain called dual domain, where you will see how can we extend support back machines to nonlinear classifiers. Very powerful classifiers. Okay, thanks.